Hello everyone, my name is Belvin and I am studying in Marwadi University in Information and Communication Technology. Currently, I am in third semester. I am recording this video and the presentation as the purpose for submitting this to the term work of the subject ICE, which is Introduction to Communication Engineering. And the topic of this presentation is time division multiplexing. And this presentation is fully guided by my professor, C.D. Parmar sir. So let's begin. So the contents of the presentation is first, we'll see the introduction to multiplexing. Then we'll see the categories of multiplexing. What is TDM? TDM stands for time division multiplexing. Types of time division multiplexing. Then we'll see what is synchronous time division multiplexing in detail. Then we'll see the digital signal service, T lines and E lines. So first of all, what is multiplexing? So multiplexing can be defined simply as many to one, or if you still want to go for a technical definition, then it's a set of techniques that allows the simultaneous transmission of multiple signals across a single data line. So what does that mean? So we have only one cable for transmission, and but we are having multiple users of let's take an example of a telephone communication. So there are two cities, like uh, like there are two cities and they are having telephone networks like this, and there are n number of users, and then there should be n number of connections that should be connecting these two cities, right? But in multiplexing, what we can do is, like, we can connect these two cities using only a single cable, and this single cable can be used to transmit all the signals within the city. So that's multiplexing in a nutshell, and we will see one of the multiplexing techniques, that is the time division multiplexing, in detail. So first, we will see the advantages of multiplexing. So just like we saw, it would decrease the amount of cabling required very drastically. So then one more advantage is, like, we can add the new connections easily. Like if there's a new user on the telephone network, then only what we need to do is, like, add the a user, and there is no extra cabling required between the two cities of the uh, uh, telephone network. So this is a diagram of overall multiplexing. Like, here we have a mux and here's demux, which stands for multiplexer and demultiplexer. So what mux basically does is, it takes n number of inputs. So there are n input lines, and it has only one output line. So it just like, switches between these inputs, and the switching is the multiplexing technique is dependent on the switching. Like for example, we are having n inputs, like which input to send as the output, and the demux would receive those output and then provide it to the related output. So there is only, so the whole point here is, like, there is only one connection or one cable between the mux and the demux. This can be two different cities or two different uh, states or whatever, but we are having multiple inputs and there is only one cable required to transmit the signal, and we are having a demux which would receive the input, which will receive the output as an input, and it would decide where to send the signal. So totally there are three different types of multiplexing. We have frequency division multiplexing, we have wavelength division multiplexing, and we have time division multiplexing. We will see time division multiplexing in detail. So what is time division multiplexing? So at different time, we are having different samples of the data which would be sent over the cable. So like here we are having user or laptop 1, 2, and 3, 1, 2, 3, and 4 connected, and the same is here. Like, the data sent by 1 should received at 1, data sent by 2 should be received at 2, data sent by 3 should be received at 3, and so on. So what we have here is, first we have the sample of signal, sorry, the user 1. Then we have user 2, then we have user 3, we have user 4, and so on. So we are not sending the entire data, but the samples of the data at different time. So the signals are sampled and then sent over uh, the cable, like for analog signals, whereas in digital signal it can be directly sent. So here the data of user 1 is sent first, then data of user 2 is then sent, then data of user 3 is sent, then data of user 4 is sent, and likewise it will maintain the order, and the mux will select the line and send the data. At the same time, the demux will also select the line to where the data will be transmitted. Like if the data 1 is sent first, then the demux will send that data to the user 1, then second data to the user 2, and likewise. So there are basically two types of TDM in on itself. Then first one is synchronous TDM, then we have statistical TDM. We will see the synchronous TDM. So here we have some theories, but we'll understand the theory using this diagram here. So what happens is, like, we are having three different input lines here, like user A, B, and C. So whenever the mux gives an output, it divides the input into a frame structure like this. So the frame size will be dependent upon the number of connections. In this case, we are having three connections. So A, B, and C. So each frame will have three data, that is A, B, and C. So suppose here the that entire frame will have t seconds of time in the t seconds duration in the output line. So suppose and the packets or the bits within the frames will have t divided by the n number of connections. In this case, we are having three. So first we have A1, B1, and C1, and it is having t seconds. So each frame would be having t seconds, but that frame would contain all the data. Like this frame, for example, mm, we are taking this frame. It's like it is having all the three, like it is having this, and this. So, but here A1, B1, and C1 are having t seconds, but that would be divided by 3 or divided by n in general case. So here A1 will be t by 3, B2, B1 will be t by 3, and C1 will be t by 3. So that uh, combined together forms a frame which would be having 3 seconds. So t by 3 multiplied by the number of connections, that is 3. So it would be 3 would cancel out each other, and we would have a frame of t seconds. So that's how the time is divided here. Then we would move forward. Like this is a video of which I performed, and here we are seeing an time division multiplexing of an analog signal. So here we are having a basic TDM trainer kit. So the uh, inputs are this is the time division multiplexing circuit here, this time division multiplexing circuit, and we have provided the input to the both the channels, and we are taking the output to the CRO, which you will see. So let's see. So if I skip a little bit forward, so these are the connections, and that connection is provided to the CRO. So as you can see, there are we can see that there are two signals here, but as we can, so this is where we are getting the output. uh, so this is the point we are getting output from, and as you can see, this is the only one output, but we will receive two signals in the CR. As you can see, this is the one signal and this is the second signal. So even though we are taking only one output line, we are getting two signals. So that means we have multiplexed two signals together and sent over a common transmission cable. So if I adjust this is a time knob. So by adjusting it, we can see the signals at different levels. So and there was another input or output taken from this trainer kit. So that is the input signal of this of the second signal. So as you can see, the input signal matches with the one of the output signal, because output signal uh, has two signals and this input signal matches with one of it. So then as you can see, I'm changing the knob of the second signal, so this signal would vary. As you can see, the size of the signal is changing due to the because I'm changing the frequency there. So that signal would be changed, and that's only that signal will change, and the overall signal won't be the overall first signal won't be affected, but the second signal would change. So we can say that the both the signals are sharing the same cable. And as you can see, again, this signal will match the second signal. So that's a little demonstration. Now let's look at an example here. Like it says, for the previous figure, that means the figure which we saw here, just talking about this figure. So the data rate for each input connection is 1 kbps. So let's draw along with it. So we have a multiplexer like this, and we are giving 3 connections, and each connection is having 1 kbps data rate, right? If one bit at a time is multiplexed, that is a unit is 1 bit, what is the duration of each input slot, each output slot, each frame? So this is 1 kbps, right? So each input slot duration would be 1 divided by, since it is 1 kilo, so 10 raised to 3, that is 1 millisecond. So each input slot will be having duration of 1 millisecond, because we have 1 kbps of input connection, and that so one at a time, at 1 second 1 kilobit will be transmitted. So if we want bit duration of 1 bit, so we will divide that by 10 raised to 3. So 1 bit will be transmitted in 1 millisecond. So multiply this by 1000, so we will have 1000 seconds, which would be sorry, which we will have 1 second, and the data, so the bits transmitted at that 1 second will be 1000 or 1024 in this case, since we are in digital. Then each output slot. So what we saw earlier, that each frame uh, would be divided into the number n, which is the number of connections. So here we will have A, here we will have B, here we will have C. Like if we name it like this, then what would be the output duration of each slot? So what would be the single slot's output duration? The output duration of all three will be equal. So if we find a duration of only one slot, we will get the answer for the rest of the two also. So like we saw, so if we are having t seconds for here, then this would be t divided by 3. So in our case, t equals 1 millisecond. So each output slot will have a duration of 1 by 3 milliseconds. So this each output slot will be 1 by 3 milliseconds. Then we will see the duration of each frame. So we can find this by two methods. Like we are having n uh, n slots within the output. So we are having three output slots because we have three connections. So we can multiply this answer with 3. So if we multiply this with 3, then 3 would cancel out and we will have a duration of 1 millisecond. So each frame would be equal, would have duration of 1 millisecond. Another way is this would always equal this in most of the cases. So each the input slot will, the duration of the input slot will be the duration of each frame. So that is 1 millisecond. That's There's all that, and we will move forward. So next we have one more example. Here what we need to find out is, here we have 4 input connections and all 4 are having the 1 Mbps speed. So we need to find the following: the input bit duration, output bit rate, and output frame rate. All right. So what we can do here is, let's take the pen. And the input bit duration, here we have 1 Mbps, 1 megabits per second. So 1 divided by 10 raised to 6. So this is a 1 bit duration, and we can simplify it to 1 microsecond. So the input bit duration will be 1 microsecond. Output bit duration. So what we have, the T here, this is 1 microsecond. Now we have 4 connections. So we have to divide this by 4. So the output bit duration will be 1 divided by 4 microseconds, right? So then we have output bit rate. So output bit rate would be uh, n times the input bit, bit rate, that is 1 Mbps, right? So we are n, we have 4 connections, so 4 multiplied by 1 Mbps equals to 4 Mbps. So the output bit rate will be 4 Mbps, right? Then we have the output frame rate. So how you find the frame rate? Like we have the frame duration, right? So what would be the frame duration? It would be 1 by 4 microsecond multiplied by 4, that is 1 microsecond, or we can directly take this, the input duration. So we have frame rate of 1 microsecond, which means that in 1 microsecond, it is transmitting 1 frame. So what would be the frames which would be transmitted in 1 second? That would be the that would be the frame rate. So here, as we can see, it is a 1 Mbps connection. That's why we are having 1 microsecond. So we would multiply 1 microsecond with 10 raised to 6. So it would make it 1 second. So 10 raised to 6 multiply by 1. So we will have 10 raised to 6 or 10 raised to 6 frames per second. Okay. Or another way we can find is like this is 1 Mbps. So we can, so this output frame rate it should be able to transmit this amount of frames at 1 second. So 1 Mbps, that is 10 raised to 6 bits per second. So that would be 10 raised to 6 frames per second. So the frame rate would be 10 raised to 6 frames per second. So we move ahead. So there is one more example we have. So the duration of one bit before multiplexing. So that is the input bit duration, nothing else. So we have 4 1 kbps connections. So let's draw it first. So we have 1 kbps connection, 4 1 kbps connections. So what would be the bit duration? So that would be 1 divided by 10 raised to 3, that is 1 millisecond, because it is 1 kbps. So the transmission rate of the link. So since we have 1 kbps connection and 4 1 kbps connections, and we have 4 total such connections, we should be able to send all those within a second. So in 1 second, all the this data should be transmitted. So we should have transmission rate to n into 1 kbps. So n is nothing but the number of connections. So it would be 4 into 1 kbps. So the transmission rate would be 4 kbps. So the duration of a time slot. So that is nothing but the output time slot. So we are having 4 connections. So the frame would contain 4 bits. So A, B, C, and D, if we name it like that. So the input duration is 1 millisecond. So the output time slot will be 1 by 4 millisecond. Then we have duration of a frame. So it is nothing but this itself, that is 1 millisecond. Okay, so now let's move forward. Okay, so synchronous Tdm, the synchronization is essential. So like the Tdm can be visualized like this, like two rotatory switches rotating at the same time, but in the opposite direction. So you can see this is the, sorry, let's take a laser pointer. And yes, so this is the connection A, B, and C. At the same time, with the output, we'll have A, B, and C. So suppose the switch right now is here and this switch is here. So it would transmit the data from A, and this would receive A. So whenever this is here, then this uh, switch would be here and this switch would be here. So this time this would transmit B and this would receive B. So whenever we are having n number of connections in this side, we would have the n number of connection on this side too. So we are having 3 connections here, so we are having 3 connections here. So as you can see, this is going from here to here and this switch is going from here to here. So this is having a clockwise direction, this is having a clockwise direction, and this is having an anti-clockwise direction. So they are rotating in opposite directions, and uh, so this should be synced. This the switcher should be synced, and so this switch would open, or this switch would open, so this would transmit the data, and this switch would open and this would receive the data. This process is called interleaving. So this is the concept of interleaving. So we'll move forward. So this is a little animation which would show the the rotation of the switches, and so both would rotate at the same time but in opposite direction. So the output would be received only by the supposed input or the conversation A should be sent to the uh, conversation A, or the person who this person A is connected to. Okay, so we will have one more example. So we are having 4 channels which are multiplexed using TDM. Each channel sends 100 bytes of data. We multiplex 1 byte per channel, and we have to show these things. So first let's draw it. Okay, so 100 bytes. In 1 byte, we would be having 8 bits. So 100 bytes, that would be 800 bits. So 800 bits per second. So we have something like this. So we have something like this. So 100 byte is sent in a second. So 1 byte would be having 8 bits. So we can say that a frame size would be 8 bits. One frame would contain 8 bits, or one frame would contain 1 byte. Because why we have selected like this? Because here we say that we multiplex 1 byte per channel. So one frame would be containing 8 bits, or sorry, we have done a mistake. We are multiplexing 1 byte. So 1 byte would have 8 bits, and we would have such 4 uh, 4 times 8 bits within a frame. So we would have 1 byte from this, then we will have 1 byte from this, 1 byte from this, and 1 byte from this. So we would actually have 4 bytes within the frame. So 4 bytes, that would be 8 times 4 bits, that is 32 bits. So each frame would be having 32 bits. Okay, so we are multiplexing 1 byte per channel. So each frame would contain 4 bytes. So 4 bytes, we have converted that to bits, that is 32 bits. So next we have duration of a frame. So each frame is having 1 byte, and each channel sends 100 bytes per second. So the link should be able to transmit 100 bytes per second. So the duration of a frame would be just inverse of that. So duration of each frame would be 1 upon 100 seconds. So each frame would be having this much duration. So if we multiply this with 100, that would be so this is the number of frames we need to pass in a second. So if each duration, if a frame is having a duration of 1 upon 100, and we want to send 100 frames, so this 100 would just cancel out, and we would have 1 second. So if we want to send 100 frames in 1 second, then the duration of each frame should be 1 upon 100. So the duration of each frame would be 1 upon 100 seconds. And the frame rate would be so we are sending 100 bytes, and each frame is having 1 byte. So in 1 second we need to send 100 bytes. So the frame rate would be 100 frames per second. And then we have bitrate for the link. So that is the transmission capacity of the cable. So we are having 100 bytes of for each link, and we are having 4 such links. So 1 byte equals 8 bits. So we have to send 800 bits per second, or so we need to send 800 bits. So, but there are 4 such connections having 800 bits. So this should be n into 800 bits per second. So n is nothing but the number of connections. So 4 into 800 bits per second. So that would be 32,000. Just a second. Sorry, it's not 32,000. 800 times 4 is 3,200. So the data rate or the bit rate would be 3,200 bits per second. Or if you want to simplify that, I can write 3.2 kbps. So here in this example, we are having something different. A multiplexer combines 400 kbps channels using 2 time slot of 2 bits. Show the output. So we are having something like this. So all this is having 100 kbps. So what would be the okay and okay, time slot of 2 bits? So first of all, we need to see how the frame would look like. So we would have a frame something like this. We are having 4 connections, so there will be 4 parts, and each slot would contain 2 bits. Let's say, for example, 0, 1, 1, 1, 0, 0, 1, 0. So previously we saw that if you multiplex 1 byte, so it would be having 8 bits or 32 bits, but here we are having one slot is having 2 bits. So 2 into 4, that would be 8 bits, right? So the frame would look like this. Each time slot having 2 bits, and so hence the whole frame size would be 8 bits. So in this case, let's first find out the bit rate of the link. So bitrate would be n times the 100 kbps, that is duration of each input slot. I'm sorry, the rate of each input slot. So 4 into 100 kbps, so that would be 400 kbps. Bitrate would be 400 kbps. Then we will see the bit duration. So we have bit rate, that is 400 kbps. So bit duration would be 1 upon 4 into 10 raised to 5. That is 400 into 10 raised to 3. So that is 4 into 10 raised to 5. This would be equal to 2.5 microseconds. If I'm not wrong. Next, we would find the frame rate. So what would be the frame rate here? So we need to send 400 kilobits per second, right? And each frame is having 8 bits. So 400 kilobits, so we need to add 1000, that is 3 more zeros. So this much should be sent in 1 second. And divide, so if we divide this by 8, because one frame is having 8 bits, so we would have 50,000 frames. So 50,000 frames per second. So if we transmit 50,000 frames per second, each frame containing 8 bits, so then we can achieve this bit rates, that is 400 kilobits per second. And the frame duration would be just inverse of 50,000, that is 1 upon 50,000. So that would be equal to 20 microseconds. So we have all the answers. So now let's move forward. This is a different thing called empty slots. So what are empty slots actually? Suppose in all the previous examples, we have uh, something to send at every time, right? Suppose like this or this. Or let's say, for example, this. We had something to send at every given time. But in practical case, we might not have data to send. Like, for example, here, the first case, the second input doesn't have any data to send. So we are having this first output slot, but the second output slot is empty. So that much time is wasted and bits in the frame. So in the third case, sorry, in the second case, 2 bits are absent. The third case, this slot is absent. So that whenever we don't have anything to send over a time division multiplexing, but the frame should be formed in such a manner that at different time, different input is there. So at the time where there is no input, there would be an empty slot. So that is empty slot. This can be solved by the statistical time division multiplexing, but uh, here our scope is just right now synchronous time division multiplexing. So this is something that is solved. This is not, but this is a problem in the synchronous time division multiplexing. Then we have data rate management. One more practical problem we might face is, like, in all the previous examples, we have seen that there is common data rate in all the input lines. For example, here we have 100 kbps for each channel, then here we have 100 bytes for each channel, and here we have 1 kbps for each channel. But what if it changes? Like here we have 20 kbps, 20 kbps, then we have 40 kbps, 40 kbps. So we have three different way to deal with this thing, to deal with this condition or situation. So first we have multi-level multiplexing, then we have multi-slot allocation, then we have pulse stuffing. So we will see each one in detail. So what is multi-level multiplexing technique? So for example, we are having something like this, that is 20, 20, 40, 40, 40 kbps. So in this case, what we can do is we can multiplex these two signals. So if you are multiplexing these two signals, then the output data rate would be n times the 20 kbps. N is nothing but the number of connections, that is 2, 2 into 20. So we have 40 kbps. So we have achieved 40 kbps, and which is the equivalent of this. So we have, uh, like uh, made everything equal, even though it wasn't at first, but we have used one more level of multiplexing. So we have called this thing multi-level multiplexing. So and now the multiplexing is possible with this thing. So this is the one case. But in this case, we are having 25 kbps and one we have 50 kbps. So here the reverse can be done. Multiple slot can be allocated for one signal. So if we look at here, then we have split this signal, this 50 kbps signal, we have split using the demux. So the reverse is applied here. So at the previous example, we have increased the data rate, but here we are decreasing the data rate. So now, why is it called multiple slot allocation? Because these three connections would have one slot, this, and this. But this 50 kbps, this single signal would occupy two slots. So we have allocated two slots for this signal. So it is multiple slot allocation. And since we have decreased the data rate by a demux, so we have 25 kbps, 25 kbps here. So we have 25, 25, 25 kbps here. So now this can be multiplied because we have equal data rate for everything. This is multiple slot allocation. Then we have pulse stuffing, but here these were the multiples of each other. So here 20 and 40, so we can multiply this with 2. Here we can divide it by 2. But here that is not possible. We are having 50 kbps, then we are having 46 kbps. So what we can do in this case, it's like we can make one input data rate dominant, the highest one. So here 50 can be the dominant data rate, and we have to make this 46 up to 50 kbps. So how we can do this? Like we can add some dummy bits to this data, and that dummy bit would actually cause the increase in data rate, that is 50 kbps. And again, we have made it all equal, 50, 50, 50. So multiplexing is possible since we are adding some bits or the dummy bits. So it is called pulse stuffing, bit padding, or bit stuffing. So these are the three different data management techniques, that is multi-level, multi-slot, and pulse stuffing. So moving forward, we have frame synchronization. So what is frame synchronization? Suppose, okay, I'm having something like this multiplexer, then at the other end we are having a demultiplexer, and we are having two connections here, and we are having two connections here. Suppose if there is no synchronization, that it may happen that this data would be received here or this data would be received here, which is not what we want. This data should go here and this data should go here. So that is what we want. So we are having synchronization bits. So this bits is added to the frame. So each frame is having one extra bit along with the data bits. So that bit is called a synchronization bit. And with the help of this synchronization bits, the frames would be in sync. Like this would not go out of sync and go to here. So, but it would be in sync, and the at the receiver side, that would be received where it is supposed to receive. So this is called frame synchronization. This technique is called frame synchronization, and this bits which we are using in the frames is called synchronization bits. So these synchronization bits will help the demarks to identify the frames. So mostly the pattern for the synchronization bits would be alternating ones and zeros. So first we have one, then we have zero, then again we have one, then again if there was a fourth frame, you would have zero, and the data bits would be here. So that is the frame synchronization. Then let's jump into one more example here. So what we have here is we have four sources, each creating 250 characters per second. If the interleaved unit is a character and one synchronization bit is added to each frame. So first, let's draw the case here. So we have four sources, that is four input connection, nothing else, and each having 250 characters, and interleaved character, interleaved unit is one character and one synchronization bit. So let's say this is the synchronization bit, and then one character is the unit. So one character, which means, so one character means each character would have 8 bits. So a total frame size would be 8 bits plus 1 bit. So that is frame size, size of each frame would be 9 bits. So we are having 250 such characters. So 250 multiplied by 8 would give us 2000. So what we have here is 2 kbps. If we have 2 kbps, so we can send 250 characters per second. So the data rate of each source would be 1 upon 2000 seconds. That is 1 upon 2 into 10 raised to 3, or we can say 1 upon 2 millisecond, or 0.5 millisecond. Now, the duration of each character in each source, so that would be 1. Okay, it seems like we have made a mistake here. The data rate of each source, it's not duration, it is data rate. So it would be 2 kbps here. So now the duration of each character in each source. So then the duration comes into picture. So it is 1 upon 2000. So that would be 0.5 millisecond. And each character is having 8 bits. So 0.5 into 8. So we are having 4 millisecond. Duration of each character in each source would be 4 milliseconds. Yeah. Now, what would be the frame rate? So we need to pass, or we need to send 250 characters per second, and each frame is having one character. So frame rate would be nothing but 250 frames per second. So, yep. Now, duration of the frame would be just inverse to this. So that is 1 upon 250 seconds. Number of bits in each frame. So, okay, so here first we saw that one character is interleaved. So we won't have 8 bits plus 1, 9 bits. We won't have something like that, but 8 bits into 4, because we are having 4 connections. So 4 into 2, that would be 32 plus 1 synchronization bit. So that would be 33. So each frame would contain 33 bits. Now here we have to do something different, because here we have an extra synchronization bit. So if it was our normal case, then we would have just did like n into 2 kbps. So that would be 4 into 2 kbps, so 8 kbps. That would have been the ideal or normal case. But here we are having one extra bit in each frame. So we need to take that into consideration also. So what we can do is, like, we can multiply the frame rate with the number of bits in each frame. So we can multiply this to 250 into 33. So we need to send 250 frames per second, and each frame is having 33 bits. Now if we calculate this, we would have 8250 bits per second. Why 8250 bits per second? Because we are sending 250 frames per second. Each frame is having one extra bit. So if we add all those extra bit, we would have 250, and 8000 would have been our ideal data rate. But since we are sending one extra bit in each frame, so we have to add this 250. You can look in that way also. So we have one more example here. This is related to the data rate management. So two channels, one with bit rate of 100 kbps and another with bit rate of 200 kbps are to be multiplexed. How this can be achieved? So we have already saw. So here we can have a multi-slot allocation. First, we can send the 100 kilobits per second, and the next, that is 200 kilobits per second, that is we do something like this. So here it would have 100 kbps. So we are having now three equal data rates, so then we can proceed to the output. So what would be the frame rate, frame duration, and bit rate of the link? First, let's say for find out the bit rate. So that would be 3n into 100 kbps, that is 3 into 100 kbps, that is 300 kbps, right? Then we need to find frame rate and frame duration. So frame rate can be obtained like this. So we have 100 kbps, 100 kbps, 100 kbps. So we need to send 100 kbps in a second. So each frame would contain, for example, 1 kb. So what we can do here is, so each frame would carry 3 bits. It would be from here, here, and here. So 3 bits would be in each frame, like this. And we need to send 100 kilo bits like this. So that would be 1000 frames per second. So each bit is each frame is carrying 3 bits of A, B, C. Let's say, for example, if we name each of them, then if we want to send 100 kilobits of each thing, and each frame is having one bit of each channel. So we need to send 100,000, or 1 into 10 raised to 5 frames per second. And frame duration would be inverse of this, so 1 upon 0.0 seconds. This would be the frame duration. Next, we have digital signal service. So like the telephone companies usually implement the TDM through a hierarchy of digital signals called digital signal service or digital hierarchy. So like as we can see in this figure, we have TDM here, then TDM here. So first we are having the signals from here, and we are having total 24 such signals, and its data rate is 64 kilobits per second. So these signals are called DS0 signals. And as the TDM is performed, these signals would be called DS1 signals. Then if we perform again TDM on this, it is called DS2 signal. If we perform TDM on this, then it will be called DS3 signals, and likewise. So here we have 64 kilobits per second, and when we are multiplexing this, it would become 1.54 megabits per second. And we will multiplex this, it will become 6.312 megabits per second. Multiplex this, and it will become this, then this, and this. So this is the hierarchy of DSS, sorry, digital signal service. So what are, then we have T lines. So what we saw here is like DS0, DS1, DS2, DS3. Those are just the names of the services. And for implementation of such signals, the companies use something called T lines. So T lines is used for implementing all this digital signals. So T1 would be having 1.544 Mbps, DS2, or it is nothing but this the same thing. So DS0, sorry, DS1. So this would be implemented with T1 and would be having this much data rate. This would be with T2 with this much data rate. So that's the given here in tabular form. So that's the T lines. Now let's see the frame structure of T lines. So T1 line. So as we saw the DS0 side, we would be having 24 such signals, and sampling would be performed at 8,000 samples per second. So that just means that the frame rate is 8,000. So we are having 8,000 frames per second. And since these voice channels are analog in nature, we have pulse coded modulation or PCM in all these cases, which would convert the analog signals into digital signals. And all those would be having 64,000 bits per second or 64 kilobits per second. So that would be 24 times 64 kilobits per second, which is performed here, and plus we have 8 kbps overhead. So overhead would be additional data rate which would be added at each hierarchy. So here there will be 8 kbps overhead, here there will be some n overhead, here there will be n kbps overhead. So here in T1 we would be having 8 kbps overhead. So now let's look at the structure of the T1 frame. So the frame, as we saw here, we are having 8,000 samples per second. So we would have 8,000 such frames, as we can see. So the data rate is 8,000 frames per second, and each frame would be having 24 slots because we are having 24 such connections, right? So we are having 8,000 frames and we are having 24 slots, and each slot would be having 8 bits. So channel 1 we are having 8 bits, channel 2 we are having 8 bits. So there would be 24 such slots, and 1 bit would be a synchronization bit. So we are having 24 slots, each having 8 bits and 1 extra bit for synchronization. So that would totally equal up to 193 bits. So one frame would have 193 bits, and we are having 8,000 frames per second. That is the frame rate. So 8,000 multiplied by 193 bits per second. So that would give us the data rate of 1.544 megabits per second. Now, similar to T lines, we have also something called E lines. So this is nothing but the same concept which the T lines uses, but there are the two systems are conceptually identical, but their capacities or the data rates are different. So E1 is having 2.048 Mbps, E2 is having 8.448 Mbps, and like that. So this is everything you need to know about TDM, multiplexing, time division multiplexing, and the synchronous TDM, T1 and E1 lines. So I hope you enjoyed this presentation, and thank you for listening.